In this video we're going to be doing some practical op-amp circuit design, so where we're actually trying to solve a real problem. Now the techniques that we're going to be using here actually come from a Texas Instruments book called Op-Amps for Everyone. It's from about 2002 and we're going to be looking at chapter 4. Now I'll just point out that although this chapter is for single supply design, it actually works for dual supply design as well, so don't limit it to just single supply design. And of course single supply meaning of course that one of our power supply rails to our op-amp is grounded, as is common in most battery powered devices. Now the example that we're going to be working through is one of a pressure sensor. And this pressure sensor measures from 0 to 4 kPa or 0 to 40 centimeters of H2O. So we can use it for measuring liquid level, or we can use it for measuring pressure differential within a circuit, hydraulic circuit for example. But the key things to see here is that at 0 kPa we get 1 volt, not 0, which is unusual, and at 4 kPa we get 5 volts. Alright, so we have this rather unusual relationship where we have a 1 volt sort of bias on our result. So what we want to do is pass that through an op-amp circuit that we've got, in this case 12 volt supply, through to a data acquisition device which has got an ADC which ranges from 0 to 10 volts. So in order to maximize the accuracy of what we can measure using our DAC, so this is effectively an ADC, we want to shift and scale. So we're going to be amplifying and biasing the signal such that we can use the full range of our DAC in order to take measurements of this pressure sensor. So the way we can do that is we can write down a set of linear equations for our op-amp. And so we can say that the output voltage is a linear function of the input voltage. So M times V in plus B. So we can write down our two equations based on the extreme points of our sensor. So 0 volts out is equal to M times 1 volt in plus B, and 10 volts out is equal to M times 5 volts in plus B. So these are two linear equations, therefore we have two unknowns and can be solved. Right, the way we could do this very simply is we could say from that top equation that M is equal to minus B. In fact, let's do it the other way around. B is equal to minus M. So we just bring M onto the other side over here. Therefore 10 is equal to 5M minus M, which is equal to 10 is equal to 4M, therefore M is equal to 10 over 4, which is equal to 2.5. And we know from this relationship B equals minus M, B is equal to minus 2.5. Right, or we could have got our calculator to do it, but just solving a series of simple linear equations there. Now within this chapter of this book are 4 cases that you can use based on the signs of our solution. So in this case we got plus 2.5 for M and minus 2.5 for B. Case 2, you'll see we've got plus M and minus B, as I've got here. So from that I know I'm solving case 2. This is the most common one we're using. Case 1 is also fairly common as well. So just based on the signs of the solution to the gradient and bias associated with our linear equations. So you would then go into case 2 based on that plus and minus in the book, and you would see this expression for output voltage, which is not very nice, and I don't expect you to be able to derive that, but this is the full expression here, noting that we could have a extra reference voltage here, or it could be the same as, sorry, not Vin, or it could be just VCC. It doesn't have to be a separate voltage, but if you've got one available, it can make the circuit design a little easier. And so we see we've got, with this solution circuit, 4 resistors that we have to solve for. R1 and R2, which is a divider on the reference voltage, which provides our bias, and RG and RF, which are our normal, and you'll see it, our input applies to the non-inverting terminal, so this is a non-inverting amplifier, which makes sense because we have a positive gradient, so we're at positive amplification. But you see the bias voltage, which applies here, is supplied to the negative terminal, so we have a subtract a bias voltage, and therefore we have a minus B, which is what we've got in case 2. Right, so we can see that that's the case associated with the circuit by examining the inputs to our terminals. So let's look at how we would go about solving this. What we've got is there are actually 2 methods that we can use. We could try and solve a very complicated set of equations, as we can see here. M equals, well, this equation here with R1 and R2 in parallel, and the absolute value of B is equal to this one. Now, this is quite difficult because we've got 4 unknowns and we've only got 2 equations. So it's going to be difficult. There'll be a lot of trial and error in that. However, making the assumption that R1 in parallel with R2 is much less than RG simplifies the calculations of the resistor values. So using these assumptions, so we can say that M is equal to RF plus RG over RG. Right, so let's write this one down. M is equal to RF plus RG over RG, just as we have here in the original reference. So let's substitute in the values that we know, which in this case is only 2.5 is equal to RF plus RG over RG. And what we can do is we could say that's effectively equal to RF over RG plus RG over RG. And therefore, if we subtract 1 over to the other side, 1.5 RG is equal to RF. So we can come up with one expression that relates the 2 values of resistance. Now at this point, nothing else in the equation or the formula tells us what those 2 values of resistance have to be. Alright, we need to use our knowledge of electronics and the circuits we're trying to build, and the fact that we use common values of resistors, or of resistance, when selecting not only RF and RG, but also R1 and R2. Right, so in this case, I'm going to say RG is equal to 10k ohms. Okay, reasonably large value. Remember that the assumption that we were making says that RG is going to be fairly big, so 10k, maybe 100k would be alright as well. And RF is equal to, therefore, 1.5 RG, which is equal to 15k ohms. Right, and both of those are fairly common values that we could buy. So those are realistic, not going to have lots of current flow, and I think they're reasonable values that we could choose. Right, so that's RF and RG solved for. So in our circuit, we would have RF is equal to 15k and RG equal to 10k ohms. To solve for R1 and R2, we now use the expression which relates B, which is this one as we see here in the Texas Instruments book. So we have B is equal to VCC RF over RG times R2 over R1 plus R2. Right, just double check that. RF over RG, R2 over R1 plus R2. Good. So let's substitute the values in we know. Just taking a note that this VCC here could be a reference voltage if we have it available. Otherwise, we can just use VCC in here. So, and sorry, that should be the absolute value of B. So 2.5 is equal to, not minus 2.5. Right, I know we solve for the negative one here, but it is the absolute value. It's equal to 12 times 15 over 10 R2 over R1 plus R2. So 2.5 is equal to 18 R2 over R1 plus R2. And we could say then that 2.5 R1 plus 2.5 R2 is equal to 18 R2. And 2.5 R1 is equal to 18 minus 2.5 R2. And therefore R1 is equal to 15.5 divided by 2.5 R2. So we have now another relationship, and I'm just going to draw a little line over there, between R1 and R2 by just simplifying that expression down and substituting in the values. In this case it's a little harder to choose the values of R1 and R2. The thing we have to remember, of course, is that R1 and R2 must be much less than Rg, so in parallel, sorry, these two values. In this case I'm going to choose R2 is equal to 100 ohms. Right, it's small, but it's not too bad. And then 15.5 divided by 2.5 is 6.2 times 100 ohms is equal to, therefore, 620 ohms. Now that's not on the E12 series, but I believe it is on the E24, or very close to, so we can actually get a reasonable solution to this. If we were to then check that R1 and R2, it's important to do this check, in parallel are equal to, so we would do 100 in parallel with 620. I get 86.1 ohms, which is much less than our 10k, and therefore our assumption holds. Okay, so assumption holds, and we were valid in using it. If we then substitute these values back into our circuit, so R1 is 620, R2 100, and we then put them into this full expression here, you will come out with V out with V in equals 1 volt of approximately 0.01 volts, and V out with V in equals 5 volts equals 9.96 volts. Alright, the reason they're not perfect is because we have made that assumption. Alright, obviously the smaller Rg is with respect to, the smaller R1 in parallel with R2 is with respect to Rg, the better our solution will come out. But for the purposes, that's not too bad. Alright, maybe we could work on making that a little bit better though. Okay, so this process again, using the Op Amps for Everyone book from Texas Instruments, you can find it on AUT online. Taken a pressure sensor here where output goes from 1 volt to 5 volts, and we wanted to design this circuit, okay, this op amp circuit, so that we got 0 to 10 volts out, suitable for supplying to our data acquisition device. We first wrote out the linear equations and then solved them for M and B, the gradient or the amplification, in the bias. From that we determined we were in case 2 by looking at the Texas Instruments book, positive gradient and a negative bias. Okay, so those two signs showed us the process we needed. We then solved for RF and RG by substituting into this expression for the gradient, and we use the assumption if R1 in parallel with R2 is much less than RG, okay, we can use this one. We then use some common values of resistors to then select RF and RG. We then moved into solving for R1 and R2 by using the values that we'd had so far. Noting if we had a reference voltage we could use in here, or we can use VCC. It will depend on your application whether you need a reference voltage. Okay, and that could be any voltage, 5 volts, 3.3, whatever you had available might work better in here, give you better values of resistors. Wandered through the equations till we got to the point where we have another relationship, used some common values of resistors in here, and then we checked that the assumption held. Alright, from there we can then substitute in, and always substitute in and check to see that the values you get out are in fact what your original design spec was. Don't just rely on the fact that all your algebra here has been perfect.